So welcome to the first IRIS-HEP Topical meeting. These will occur once or twice a week, depending. We try not to get them too crowded, but today and tomorrow we both have time slots. I think most of you are probably on our announce list, and that's where we'll be doing most of the advertising for these talks. Everybody's welcome. So if you see a topic that somebody not associated with IRIS-HEP or not on the mailing list or just might be interested, please do drag them along. Just as a word of warning, we're recording these and we will eventually post them on YouTube. But I hope that will not, everybody will feel comfortable enough to ask Ryan lots of questions. So today, Ryan from Argonne is going to talk to us about FuncX, a function serving platform for the HPC. So Ryan, why not take it away? Hopefully people, if they have questions, will stop and ask them. And there's also some time set aside at the end for more generic discussion about this as everybody wishes. Ryan, if you're trying to speak, you're muted.
There we go. That one should be working.
That's beautiful.
Perfect. And hopefully it's still working now. I'm not too sure how it muted itself. We're good?
Yeah.
We are.
Okay. Well, firstly, thank you very much for having me. Like Gordon said, I assume it was Gordon. My name's Ryan Chard. I'm a postdoc at Argonne National Lab, based in Chicago. It's a beautiful day in Chicago. It's actually a snow day today, so Argonne's shut, but that's all right. And yeah, so I'm a postdoc there. I work mostly on research data management systems, automation platforms, and machine learning inference. And I've recently segued into this FuncX platform with one of my students, Tyler, and a high-energy physics convert, Anna, who I'm not sure is actually on the call, but she may be. Yeah, so this talk is about FuncX and work that we've been looking at doing on function serving for HPC. And I guess we'll just jump straight in. So yeah, like I was saying before, which might have been muted, I know nothing about high-energy physics, so you might need to draw your own parallels from my use cases into yours, or we can discuss this later on about how this actually lines up. So as a quick outline, this talk really covers some introductory motivation around why function serving is important and the discrepancies between high-performance computing and current use cases for what scientific analysis requires, especially in the domains of biological research, genomics, and some recent machine learning work, and a lot of light source science work. So I work quite a bit with the advanced photon source at Argonne in groups here. Yeah, and this is really about FuncX, so I'll introduce what FuncX actually is and how it can help, and then we'll go over its implementation status, which I will admit is relatively early. So we started this project maybe a few months ago, and we have a working prototype, which I'll discuss with these preliminary applications. But I need to stress that it's not completely fleshed out. There's especially one component of it which needs some work. But yeah, so we'll just jump straight in. Firstly, this is most of the Globus Labs team. So I'm part of Globus Labs. Globus is the big data management system built out of UChicago, PI'd by Ian Foster in the top right there. And yeah, I'm in the bottom left. We're quite tanned one going by this picture. And Tyler, the student that's working on this, is next to me, and Anna, our HEP convert, is next to her. Cool. So just for some motivation, next-gen data, especially in biological research and the advanced photon source, is really exploding. And it's starting to overwhelm the finite resources available to many of these domain researchers. So often they'll have a local cluster or something along those lines. And as these data generation rates and velocities just continue to explode, it becomes unmanageable for these local resources. So pretty much every scientific domain could now benefit from access to HPC resources. So at Argonne, we've got the leadership computing facility with multiple supercomputers, and they're pretty difficult to use most of the time. So we're looking at ways to actually allow these new instruments that are generating truckloads of data and different domain scientists to actually be able to use these things. But there's a bit of an impedance mismatch, if you will. Essentially, these HPC systems are designed for extreme scale workloads, simulations of the universe, really large analytical workflows and that sort of thing. Whereas a lot of domain researchers, they have really bursty requirements, which isn't typically ideal for HPC platforms. So I've got a plot over here on the right about some genomics research I used to do, where we would host scientific gateways for different genomics platforms. This is looking at 6 of them, and it shows the number of jobs that were submitted for each of them each day over a 150-odd day period. And as you can see, it's very sporadic, which isn't really a great match for HPC systems. In other examples, using a scanning electron microscope, generally these don't run 24/7. They'll run when a worker's there and when the samples are actually in the machine. But while somebody's changing the samples, essentially no data is being generated, and if they've provisioned HPC resources, they're being underutilized, which isn't good for anyone because other people can't do the research, and it's not good for, say, the ALCF, Argonne's computing facility. It's not good for them either because it's not showing high utilization. In terms of the advanced photon source, beam time is pretty rare. So I work with a neuroscience group. They get beam time once every maybe 2 months or so. And when they've got beam time, they're generating a lot of data, like 20 gigabytes a second. I know that's not a lot to you guys, but it's a lot to them. It overloads their local capabilities. So they need to use HPC, but when they're swapping samples, when they're trying to realign the beam because it's gone out of sync, these resources are wasted. And another thing around this is research is becoming increasingly interactive. So you see how popular things like Jupyter are getting. These systems really need to be able to exploit HPC research or HPC resources on demand at scale, but that really isn't there at the moment. So there are also a couple of other barriers to HPC. So I mean, if we keep thinking about things like cryo-EM machines and the APS upgrade being improved and generating more and more data, there's a massive influx of new users that potentially aren't so technologically savvy. They've probably never used HPC systems before. And these systems are quite complicated, so they're not the most user-friendly. They've got a variety of different platforms. I mean, programming for a Knight's Landing machine is completely different to a GPU-based machine. They've got steep learning curves, as I learned with one of my genomics students last week. I couldn't understand why they couldn't deploy a package on a Singaporean supercomputer, and it's because they never knew that package management, like module list and that sort of things, actually existed. So they were using the wrong compilers. Generally, there's an assortment of interfaces. At Argonne, we use mostly Cobalt, which is an in-house scheduler, but there's a variety of these. And often it's quite difficult to even acquire time on these machines, let alone actually submitting your jobs to it, which can take upwards of an hour just to get the resource that you've tried to provision. So really, these small on-demand tasks aren't a massive priority to many HPC systems. I've been told by ALCF that it's not their mission statement to deal with these small jobs. However, thousands of these small jobs are definitely an HPC problem. And we need new ways, essentially, to actually deal with these things and accommodate this new influx of users that potentially haven't used HPC before. So, serverless computing. I don't know how much you guys have heard about this, but it is all the rage in all of computer science and especially business IT. It's essentially a way of outsourcing your infrastructure management. So it's a lot cheaper. You only pay for the resources that you're actually using. It scales almost infinitely on demand. And the backbone of this, so at least one of the large submodules of serverless computing, is called Function as a Service, which is a really simple way to deploy small codes at scale. So pretty much every large cloud provider has a function serving platform, Faas, if you will. So Amazon's got Lambda, Google has Cloud Functions, Azure is the same, and then there's OpenWhisk. which is an IBM solution, now Apache. But essentially, the plan is that you pick a runtime, so whether it's Python 2, Python 3, JavaScript, R, it doesn't really matter, and then you write a code in that runtime. And that can be a very small code that executes for tens of milliseconds or for up to, I think it's now 15 minutes on Lambda. And then you deploy this thing, it gets containerized and deployed on cloud infrastructure, and then every time you invoke it, it's going to be served in approximately a couple of hundred milliseconds. And they'll run at scale. If you invoke that thing 1,000,000 times, it's going to launch 1,000,000 containers for you. So it's really nice, it's on demand, it's low latency, and it's not restricted to these small tasks because you can sort of compose these things into solving very large problems without ever touching any of the underlying infrastructure. So function serving for science, this is really where we want to go. I feel like a lot of the benefits that business IT is seeing with the simplicity of use can be sort of pushed on to scientists as well, where they don't need to worry about the barriers that exist to using HPC resources. And instead, they can focus on just getting their code deployed and using it when they need it at scale and on big machines. Function serving can support an entire new generation of users and applications. There's a number of applications that don't fit well on HPC, like machine learning inference, but these benefit from HPC resources. And it provides a number of new opportunities for optimizing these tools and workloads. So in terms of removing barriers, Faas can really make HPC accessible. The way Faas works is essentially you abstract all of the compute environments. The user only ever sees the function code. They never worry about what machine it's actually deployed on or what infrastructure is really running that machine, what queue subs have to go on, what module loads need to happen before you can actually use this thing. The runtimes, or essentially the executables, are containerized. So all of the dependencies are encapsulated in that. One benefit of that is you can move between different machines relatively easily. You could put it on Theta at Argonne and then move it to Cooley the next day with very little issues. And I mean, the side effect of this is once you've got these containerized runtimes and executables, you can really share them around and reuse them. So in terms of the advanced photon source again, the tools for reconstructing a tomographic image are essentially the same between the different beamlines. I mean, there's some nuances there, and a lot of the beamlines aren't doing tomography, but generally, if there's a library of these things and you can just pick and choose which ones you want, it really simplifies use and promotes sharing in terms of best practices. And yeah, Faas services can provide secure programmatic access. So you don't, I mean, provided we support the necessary security features such as multi-factor authentication, it's not a big problem with actually interacting with these machines. So these can provide all of the auditing that's necessary, and yeah, just really make all of this a lot easier to actually use. In terms of supporting new applications, so being able to provide short duration and low latency tasks would be relatively novel for HPC infrastructures. It would allow the use in real-time experiments, so actually guiding experiments. So with the APS, one group I work with tries to, well, one group does thresholding on images as they come off the beamline and need to know when essentially they can stop taking an image of a certain protein. And another one wants to immediately realize if the beam is actually on the image or not, because it's not always intuitive whether or not you're taking an image of the sample or whether you're getting some of the resin that's holding the sample. Interactive computing, so Argonne's recently deployed a JupyterHub instance, and being able to back this thing on and let people scale their applications very easily would be a massive benefit. Machine learning inference is another topic close to me with DLHub, our data and learning hub for science. This is a machine learning inference platform where we deposit models and then try to run them on HPC, because generally these things, they take hours to train but then milliseconds to run for an inference. So being able to actually deploy them and use them within live simulations and with low latency is extremely valuable. And then similar to real-time usage, stream processing, that's a growing demand with how much data is being generated. You need to actually know what's in that data before you commit to storing it. So it's a useful thing. And Faas also provides a number of optimization opportunities, especially around utilization of the machine. So one thing I recall talking to Anna about, our high energy physicist, was being able to exploit locality when sending queries to different data sets, and being able to actually send the query to the data set rather than bring the data set to some compute. So being able to actually allow multiple functions to share a single data set and a cache is something quite interesting that we're trying to pursue. There's a number of opportunities for optimizing the performance of these functions in terms of sharing runtimes and being able to decrease the latency of how long it actually takes to invoke these things. And then also in terms of the utilization perspective, these functions can scale quite well. So we can start exploiting things like backfill queues in these HPC resources, which are essentially otherwise idle resources that potentially there's not enough resources to fulfill some large simulation job. So they're sitting there just idly, and we can start expanding into that and preempt our workloads and resubmit them somewhere else if they fail. So that's a really interesting perspective that we want to look at as well. And really, it's all about using these HPC investments for new problems and being able to get more value out of them from the infrastructure side, which is kind of fun. Okay, so FuncX. So I'll again reiterate that this is in the relatively early stages of development, but our entire goal is essentially to build a secure and on-demand way of serving isolated functions for HPC resources for the masses. So we really want to enable this so any user can come to our platform, define a function, and then easily be able to be running the stuff on large machines. The way this works is really we want to abstract the infrastructure. So we don't want the user to have to worry about what machine they're actually running on. We just want them to worry about their function, whether or not it works, and whether or not it does what they want, and then just invoking it on demand when they need it and scaling out. And then a side project on this is to really focus on establishing a library of these functions so we can encourage fair reuse and reproducibility of people's work. So if we can provide credit to some person for creating a function that's used by the entire community, that's valuable. Yeah. Okay, so to try to get some context here, I'll try to define functions and runtimes because this all gets a little bit confusing. Functions, the easy side, this is essentially just a small executable code. So it might just be one Python function that says hello world. It could be something that iterates through some data and runs queries on something. I don't know. It could be anything. It's very open-ended to what this thing does. Generally, they're short duration. So Amazon, there used to be a 5-minute cap. I'm pretty sure it's 15-minute caps now. But there's some short duration task that isn't going to run for hours. It's just some lightweight piece of code that accepts some input, whether it's JSON or binary, and then returns some output. And they're invoked on demand. I've got a comment here saying that it's stateless, which essentially means that if you run a function and it generates some output locally, and then you run the function again, you can't expect that that output's going to still be there. So potentially this state is written to a function on one machine, and then the next function is served from a different machine, and they don't share that state. So yeah, that's what we consider stateless in this. However, we really, for the scientific purposes that we have, we need to be able to support writing out or persisting sort of outputs into shared file systems and that sort of thing. So it's not entirely stateless where everything you do in that function is one-off, but yeah, so we provide support for persisting those outputs as well to some degree. And then runtimes. So a runtime is essentially just a container, so like a Docker container of the libraries and dependencies that are necessary to run a function. So this could potentially be a list of pip install packages. Maybe you need the Globus SDK in your function. So we will wrap that up into a runtime, and then your functions will be able to execute in that runtime because all of their required libraries will exist in there. Another purpose of this runtime is to really isolate a function execution. So if you run your function, it's only ever going to be run within this container environment. It's never going to have root access to the underlying HPC resource. Another part here is that you can serve multiple functions within a shared runtime. So one of our goals of these runtimes is to essentially multiplex the function execution. So if you invoke your function twice, potentially it could be served twice within the exact same runtime or this container. So that's one of our goals. and then being able to warm these runtimes for rapid serving. So if you execute your function once, that function will, or that runtime will run within, the function will run within the runtime, and that runtime will persist for some number of minutes. So next time you invoke your function, it will end up in the same place, and that will already be there. It will be alive, and your function code will already be inside that runtime, so it will execute. Cool. Okay, so how do we actually do this behind the scenes? So in terms of executing functions, we've really underpinned our system to a parallel scripting library called Python. So this, called Parcel. So this is a Python parallel scripting library. It's developed at University of Chicago. It's got a lot of advantages which we get to take advantage, we get to exploit, and it simplifies our life a lot. The general idea around Parcel is that you can annotate Python scripts. So this is getting a little bit away from how we use it, but I've got an example on the right there where you define an app called, or you define a function called hello, which simply returns hello world, and you mark it up essentially. You annotate it with that little Python directive saying @Python app, and that means every time you invoke hello, like you do in that print statement, Parcel actually intercepts that execution or that call to that function and starts dynamically creating a DAG of how these different apps connect together. And then it goes and takes those functions and executes them on whatever resource you've told Parcel to be executing on. So Parcel really abstracts the execution of different apps on a wide variety of resources. You can use it on clusters, clouds, grids, all sorts of things. There's providers for many different queuing systems or many different cloud providers. And a nice feature is that it supports secure authentication. So you can still use your Argon crypto cards to submit a job to Cooley via Parcel. And it's as simple as running that hello world little app, and it will automatically go and push that off to a big machine and run it there for you. So another nice feature of Parcel is that it's got unique executors to meet the requirements of unique applications. So there's a high throughput executor, which is currently used for protein docking, where you submit thousands of different jobs, and it will go and run them all in parallel. There's an extreme scale executor, which is really designed for massive MPI-based jobs, and it's been shown to scale to millions of tasks. So they currently use it for cosmology simulations. And then, more importantly to us, there's a low-latency executor, which has been designed specifically for interactive jobs. I've got down here an example of how it sort of abstracts resource integration. So essentially, for any of these executors to submit to a different machine, all you've got to do is define a different config file. So this config file is using the high throughput executor, and it looks to be attaching to the Stampede machine. Actually, I don't think this is quite fully configured, but that's all right. You specify that it's going to use a Slurm provider. It's got a local channel, which means it's not actually doing this remotely. It's going to execute locally. But this is all you need to do for it to start submitting jobs to Stampede, which is really nice. So we can leverage a lot of this stuff behind the scenes to allow FuncX to execute jobs on whatever resource we want. Another nice feature of Parcel is that it scales quite well. So this is some comparison with Parcel's different executors, high throughput, its extreme scale, and its low latency. It doesn't have its low latency one here, but this shows how well it scales compared to other Python-based approaches, and it's been shown to scale up to 1 million tasks, which is really nice. And yeah, it exceeds other Python-based scaling mechanisms, which is great. Probably more importantly to us, so we don't envision having millions of tasks immediately. However, we do envision having real-time tasks very quickly. So the low latency executor has really nice latency and consistency. So we've got this plot here of the low latency executor and the other executors, as well as IPython parallel and Dask. And on the left is the thread pool, so that's just executing locally. And you can see the orange one there, low latency it's about 3.5 milliseconds, but it's extremely consistent compared to the other ones. So it's perfectly suited for our task, and we get a lot of benefit out of using Parcel to accomplish this. The other system that's sort of underpinning our FuncX work is Globus. Obviously, I'm part of Globus Labs. I think people would frown if I didn't use Globus. But in all honesty, Globus simplifies a lot of this, especially in terms of authentication, logging, identity management. We get to outsource all of that. And then on the side, we get to exploit its data staging and data transfer mechanisms. So obviously, a system like this, where we're going to be running tasks on a supercomputer, and generally a multi-factor authenticated supercomputer, we definitely need to know who the user is. So Globus lets us outsource all of this. They integrate with a number of identity providers. You can log in with your UChicago email, your Argon email, your Gmail, and it will ensure that's you every time, because it requires you to pass tokens every time you want to either create a function or invoke a function. So it's got a lot of access control built into it, which is great. And then the other thing, which I didn't really mention earlier, but those runtimes are essentially large files. So the way our process works is we start with Docker containers, but Docker isn't generally allowed to execute on HPC resources. So instead, we convert these containers, these runtimes, into singularity images, which are then on the order of a couple of gigabytes. So we need to actually move these things around, and quickly, if we want to be running these things relatively fast after the user publishes them. What was that sound? I don't know what that sound was. Hopefully I'm still going.
Somebody leaving, don't worry about it.
Okay, perfect. Good. Yeah. Okay, so our prototype. So at the highest level, our prototype is really just three components. There's the web service, which gives us a secure interface to interacting with our system. It's all Globus authenticated, so you've got to pass tokens in. We know exactly who's running what and how long everything's running for. We track everything. We've got the site manager, which is deployed at the HPC site. This is essentially a parcel code that connects back to our web service and will receive jobs and then manage their execution over different runtimes. So a real key component of this is the site manager, because it's got to manage these different runtimes. It's got to deploy them on compute nodes when they're available. We've got to scale up, scale down, get rid of used runtimes, that sort of thing. And then there's the node manager. So the node manager is a lot of the secret sauce here, which we're still working on. That's definitely our main future work component. But this is really focused on managing functions within a runtime. So the site manager will receive a job from a web service and then pass it into a runtime, and this node manager operates within the runtime to accept that job, set up a sandbox for it to execute in, and then run it. So yeah, this implementation status is still ongoing, definitely. Okay, so in a little bit more detail, the web service. So essentially it's a REST API just to create, invoke, delete functions. Where this already exists, so this is running. Actually, unless my student's taken it down. We've got a CLI and an SDK, so command line interface and software development kit, which it integrates all of the Globus auth, so you don't have to worry about passing tokens. You've just got to log in when you first use the CLI or SDK. It will acquire Globus tokens and then automatically append them to every request you make to the web service. So another key component is, in addition to creating and invoking these functions, is we create runtimes. So when you define a function, you also need to specify your requirements for that function, so the pip installs that need to happen before it actually executes. And then this gets Dockerized, pushed to the Elastic Container repository on Amazon, and then converted into singularity images, and then essentially pushed down to these different site managers. We keep track of what these requirements actually are, so we can sort of reuse containers. If both your container or your runtime or your function and my function both install the exact same packages, there's no point in us having an additional singularity container sitting on that machine. We just need to map that those two functions can run in the exact same thing. Yeah, it all relies on Globus auth, so that's great because it allows us to log usage and keep accountability, so we know what users are doing what. And in addition to that, we keep track of what these functions are actually doing, like how long they're running for, because this is really, really important to us knowing how, what resources we need to provision for the different functions and how long everything runs for, so we can start estimating how we should actually be controlling these systems. And then we've got a parcel executor up there, which is essentially a set of parcel interchanges. We don't go into this in too much detail, but the parcel interchange is pretty much just a zero and queue pipe, so you can push jobs onto it, and then that gets received by the executor sitting at the site manager. So that low latency executor or the high throughput executor, whichever one's running, will receive those jobs from the interchange and then start executing them on whatever site that site manager is running on. So the site manager, its main responsibility is to manage runtimes. So you deploy this thing, like I will log into Cooley or Beta or something like that and run this thing, and then it will retrieve all of the containers that it needs to be operating on, or it needs to be deploying all of these different runtimes, and it will keep a local repository of them so it can spin them up very quickly. Then it deploys these things. It uses parcels to deploy these things, so it actually it bakes in the scalability of these things, of these functions, of these runtimes. Sorry, I can't believe how many times I've confused that. And it will auto scale them. So if one thing's being, if one runtime's being used a lot, it will start provisioning more and more of these runtimes. Or once a used runtime is sat there for a while and hasn't been invoked in a little bit, it will spin that down and sort of give those resources back to the system. So a caveat here we should point out is that currently this is assuming that the existing system assumes there's only one site manager. So we don't have sort of multiple interchanges sitting on the web service. Instead, there's just one that's sitting at ALCF on Argonne, and it's backed by Cooley, I believe, and that's receiving jobs for everyone. So if you submit a job through FuncX at the moment, that will be run as my user on ALCF if you have permissions, which you probably won't because I need to whitelist you. Later on, we envision deploying this as a multi-tenant solution, so we would run one at ALCF, but it would take your credentials and then deploy them as you, essentially, which would be really nice. We're still in talks with ALCF and UChicago's RCC about how we actually want to do this, whether we just want to do the account management or the allocation management ourselves and then sort of pass that on, or whether we actually submit these jobs on the user's behalf. I don't know, we'll see where we end up. And then the node manager. So this is definitely under construction. The existing platform doesn't really assume there is a node manager. It just manages the runtimes and then deploys one function in a runtime as itself. There's no sort of multiplexing within the runtime itself. It's instead just run the function in a runtime. That's all it is at the moment. However, we would ideally have this deployed within the runtime itself. So each runtime would contain a node manager. This would connect back to the site manager and sort of receive functions, receive serialized versions of this function, and then it would be responsible for creating the isolated sandboxes within the runtime, so we can deploy multiple functions within one runtime rather than just do one at a time. I've looked at a couple of ways to do this. Initially, I assumed I would use Linux containers within the actual sandboxes to make the actual sandboxes. However, I had some issues with that, so I'm thinking we're just going to end up using directories and user IDs. So every time a function comes in, we'll create a new user, make a directory for that function to execute in, and then set permissions on that directory so only that user can access it, which gives us those isolated sandboxes where two functions can't interfere with each other. The node manager also needs to be doing some data staging, so bringing the data to itself or something along those lines, and managing the local cache so multiple functions can share that data set. Okay, so some preliminary work, the exciting stuff. So I've got 3 use cases here which are really motivating this work, and we've deployed prototype implementations for each of them, which is great. They all seem to be working. But yeah, this is sort of where we're going. So we've got DLHub, the Data and Learning Hub for Science, which is our machine learning platform. Globus Automate, which is a project I've been working on for the last couple of years around research data automation. And then Tyler Skluzacek, our PhD student, he's been working on Extract, which is a metadata extraction pipelining system to sort of understand file systems and clean up data swamps, as he calls them. So yeah. Okay, so quickly, what is DLHub? The entire purpose of DLHub is to really make machine learning more accessible. So it allows users to publish models, machine learning models into them, and then allows other users to use those models with little difficulty. So we take these models, we deploy them on different infrastructures, and then expose a REST API to let other people actually invoke these models. Why were we doing this? It essentially came about from a couple of machine learning experts in our group who found that a lot of machine learning research is being published, but the models that people are publishing on are not exactly usable. Generally, if they are actually put in a Git repo or something, they're not trained, we don't have the data sets. So we wanted to build some infrastructure that would let users publish their models and host them, give them a DOI, reference to them in their papers, and then allow other people to actually use them and build upon them. So be able to download these things, be able to put their own data into them. It's really our entire motivation around this. And this example on the left is actually a real-time image tagging project from the APS. So knowing whether or not these images are on the beam or whether or not they're currently missing that actual information. So how it works with FuncX, it actually plugs in really nicely because models are pretty diverse in themselves, so we have to containerize anyway. It really relies on low latency execution because we want to be able to run these things in real time. Currently, DLHub serves on a Kubernetes cluster, so we deploy the containers on Kubernetes and then do inference from there. But training requires HPC resources, which we haven't really fleshed out. So that's where FuncX comes in, because it lets us do essentially both of these things through one system, and it provides much lower latency than our existing implementation, and a lot more reliability as well. So it's really beneficial to us to be using FuncX in this example. Yep.
Yeah, on that slide, I just want to ask a quick question. So it sounds like they would have a significant amount of data, all this image data. Where is that stored, and how does that interact with the functions that are running, or is that just shipped over the wire as an argument to each call of the function?
Yeah, no, that's a good question. So the way DLHub works is this is entirely hosted at Iron. If you pass in a file pointer, which is typically a Globus pointer, okay, wait, maybe I should step back a bit. So getting data into DLHub can be passed in through the command line. You can pass in, or through the SDK, you can pass in JSON blobs, you can pass in pickled files. That'll just go straight through, so it hits the web service and gets passed down into the actual container running the model. However, if you want to pass in a very large data set, we require you to do it through Globus. So attached to DLHub is something called Petrol Cube. Oh wait, sorry, Petrol. Petrol is our 1.7 petabyte store, about to be doubled to 3.2, I think, actually, no, or maybe 3.5. But yeah, that sits right next to this thing. So the way it works is if you pass in a Globus ID or Globus URL, it will stage the data to Petrol and then pass in the stage location to the model, which then does an HTTPS download using your token to actually get that data into the model's execution environment, so into its container. So yeah. Does that make sense?
Okay, so for large data sets, you pass in basically a URL, copy it locally into the environment, and then run on it.
Yeah, which isn't ideal for very large data sets, but we haven't had that problem just yet. I think the biggest data set we've actually used as inputs is on the order of tens of megabytes, so it hasn't been a big problem so far.
Okay, thanks.
Ryan, what if you have a data set already on the parallel file system of the machine?
Yeah, so I should say that's not a problem at the moment because our Kubernetes cluster doesn't have a shared file system. It's, yeah, I mean, that is something that we want to be doing, and that's something that FuncX is trying to solve, where we run these things on the actual HPC resources that do have a shared file system. But our Kubernetes cluster doesn't yet. Our intention is in March, I believe. It just got pushed back to March this morning, that Petrol Cube, our Kubernetes cluster serving these machine learning inferences, will mount Petrol. So it will have the 3 petabyte store attached to it, and then you would just pass a local pointer to it, and it would start acting on it. Does that make sense?
Yes, thank you.
Cool. Okay, just to quickly start wrapping this up. Automate is another use case that we've got here. So essentially, it came about from Globus wanting to replace their monolithic data publication system. And by data publication, I mean move some data set to a persistent store, catalog it, set access controls on it, share it with other users. They wanted to move from their monolithic publication platform into a sort of microservice-y platform, and they needed some automation framework to actually compose these different publication platforms and execute them reliably. So I jumped in at the first part of this to build out the initial prototyping, and I quickly started reusing this thing or repurposing it for end-to-end automated analysis pipelines. This isn't terribly important, but my initial use case was neuroanatomy research. So this is using the advanced photon source to construct brain mappings, essentially, so making graphs of where all of the neurons connect. Generally, this generates about 20 gigs a minute when they're actually using the beam time, but the beam is notorious for going out of line, so they'll use it for 5 minutes, generate a bunch of data, and then suddenly not be able to use it for the next hour. So this is the automation flow that we sort of implemented in Automate, which is take data from the APS, move it through a couple of local machines, and then push it over to the ALCF where we start doing the reconstructions, get some human in the loop previewing going so they know whether or not they're using the right thing, and then push those reconstructions, those big reconstruction jobs out to the leadership machines, and then publish this data. So this was achieved initially with a pretty haphazard remote execution system that I put in place. And FuncX really provides us a much more reliable and robust solution for performing those jobs at ALCF. So that's where we're plugging this in at the moment, and it seems to be working really well. How this all comes about, it really gives us a secure and reliable remote execution platform, much more so than what I previously had. And it lets us compose these pipelines of reusable functions that we can then share between different beamlines. So other beamlines can start exploiting the work that Bobby's group have done on tomography and 3D reconstructions. And really, it takes away the complexity of the HPC integration from the domain scientists. So they don't really care about what machines it's actually running on. My system can deal with all of that. And yeah, they just get on with work and start seeing results flow back from these Automate flows, which is great.
Right, Brian. Sorry to interrupt again,
no, that's right.
but going back a slide. So these are larger data sets. It sounded like maybe 100 to 200 gigabytes or something from one run. And if I look at this flow on, I think, the previous slide, it looks like you move the data into some repository, then FuncX has direct, or disk system, and then FuncX has direct access to those files. Is that how that works?
Yeah, that's exactly how it works. So this one is not using the Kubernetes cluster. So DLHub was using Kubernetes to host their machine learning models. This is just using the straight supercomputers at ALCF, and they've all got a big data transfer node that has a shared file system on it, DTM Mirror, which is, I don't know, 15 petabytes or something like that. And we just transfer data straight into it and then start invoking functions on those data sets. Yeah.
Okay, perfect. All right. Cool. Thanks. That was what I was looking for, was how you're handling that sort of thing. And maybe Mark's question was pretty similar.
Yeah, makes sense. Cool. Yeah, I guess that's much more applicable to you guys with the size of your data sets.
Yes,
okay,
exactly.
Final use case. This one isn't terribly important, but it just really shows about pushing functions to the actual data. So this is Tyler's work where he wants to drain the data swamp. So his motivation is that essentially a lot of file systems are complete messes. Many files don't have extensions. You have no idea what's in a lot of these things. And his work is to go and automatically create catalogs of what's happening in this data and let people search over them based on what actual metadata he can pull out of them. So he's got a whole set of extractors which run on a file and then pull out some metadata. So I've got an example down here on the right about his map extractor. If you give it a map picture, it automatically runs this extractor that will identify what components are actually in this map. So in this, it sees that it finds South America and Africa, and then starts tagging this with metadata information about what places are shown in this map. So you can search over these things. It's a really cool project. However, he's got a problem where currently this thing runs on the cloud, or it used to run on the cloud, and moving large amounts of data into the cloud wasn't necessarily feasible. So to actually run this at scale, to apply it to an entire petabyte store, requires that you push this function or these functions down to the data. So this is the use case we're working on at the moment with him, to get FuncX running all of his extractors at data sets so we can essentially process these input files or process each file in place without moving it out of there, and using FuncX to sort of abstract what machine it's actually running on, so he doesn't have to worry about where he's pushing these jobs. It will just find resources, maybe exploit backfill so it can do it in downtime, and then start really creating these catalogs, which will be a lot of fun. So future work, definitely we need to finish this node manager implementation and sort out sandboxes so we can serve multiple functions within one runtime. We're always looking for new use cases. If anybody has anything that they're intrigued about, I'd love to get in contact and start working through something. And yeah, definitely multi-tenant solutions. So like I said, we're chatting with RCC about how we'd actually do this, which will be great. And yeah, standing up these things to serve essentially communities so we can simplify everybody's life. Cool. I went a little bit over time, I think. Yeah, sorry about that. But hopefully that made some sense. If you've got any questions, let me know.
Ryan, thank you very much. Don't worry about the overtime. We asked a few questions, so surely we slowed you down. Are there questions?
Yes, I have a question. You mentioned at the beginning, so it's nice that you can compose complex pipelines from simple functions. We might find ourselves in the other situation that we have a monolithic large application that we want to decompose into smaller bits and pieces. And I wonder if you have experience or any suggestions on that.
So I mean, this is a common problem that I've faced as well, especially my neuroscience group. They used to just have one script that they would deploy to do everything. So it would create previews, it would identify center files, and then it would perform the entire reconstruction, and then it would try to start stitching everything together. The problem they had with this was often the center value would be misaligned, or it wouldn't find the best fit center, and then it would perform a reconstruction and waste a lot of time and resources on reconstructing something that doesn't work out. So their work actually lended really nicely to this, because essentially their monolithic system just made calls out to a bunch of different functions. So it was very easy. It was trivial to go through and break those out into their own little components and then flush them through the system. And there was a lot of benefit to this, because it allowed us to put in our human in the loop steps, so actually validating that these center values are actually useful, and then being able to go and correct those values before wasting their compute time, because they have allocations on these machines as well, and if they go and run things for multiple hours and then don't get any useful results out of them, it's a complete waste of everybody's time. So yeah, I mean, it's definitely a big problem, and something that I think people are starting to lean more towards now with microservice architectures and serverless computing and that sort of thing. Being able to run things reliably by themselves is really advantageous to a lot of people.
Great. Of course, our field to do that, since we're all very comfortable with the 100 or 200 megabyte executable.
Good.
Entertaining.
Oh, it'll be interesting to see.
Go ahead.
Oh, sorry. I was just going to say it would be interesting to look at one of these problems. I really have no experience with it, so yeah.
But this would be more for the analysis use case, right, Gordon? I mean, I can't really see this for anything that we use our 200 megabyte executables for.
I think the place something like this is much more suited for is the analysis, the end game, the analysis use case. You can see something like this for these 200 megabyte images. Those, I assume, we're both talking about things like reconstruction, for example,
right? Mm-hmm.
Which is essentially a collection of different algorithms. And one could imagine having those split out, so the algorithms that are time intensive end up having many instances, and this is sort of like taking the multi-threaded versions and exploding them outwards. But doing that is so much more tricky, because you have to move so much data around I mean,
And there's
everything is built around this shared memory model, and moving to a scheme where that is not, the data bus, this shared memory the shared memory is not the central mode of communication would be a huge amount of work, I think.
Yeah, that's interesting. I hadn't thought about shared memory architectures before. To put a lot of constraints on. You'd think it would be achievable still.
Yeah, I mean, sorry, go ahead.
Kind of gets rid of the stateless thing, but go ahead.
Right. I don't know that it's necessarily suited. I mean, I think it would be more interesting. There may be other ways to take advantage of that are, FuncX is meant for one particular type of thing.
There are other
people that were
problems.
Right. Other people were trying to cut in, or Liz, did you finish?
I had a different question, but I'll let other people go first.
Okay, well, this will be quick. The problem that you were leading with in your slides was to handle the burstiness, and endgame analysis has a lot more burstiness than HEP reconstruction jobs. So, but instead of framing this as a negative, that this is less interesting for reconstruction, it should be framed as a positive. This is very interesting for analysis systems.
Okay, so that leads into my question. If this was going to be a general platform for HEP people to do analysis, would they all have to have Globus accounts? And who would pay for that?
That was my question.
Yes.
So the nice thing about this system is we use Globus for identity management. You don't need a Globus account. There's no paying for Globus subscriptions. I assume CERN already does that, but I don't know. That's not my role here. So yeah, really, if we had a resource that was restricted to users with CERN accounts, where we could use Globus to authenticate that they actually had membership at a CERN, or they had CERN accounts, and then just restrict execution access based on that. So yeah, that's not really the way the Globus sort of integration works with this. Does that make sense? I don't know if you guys have much experience with Globus and all of this.
I understood the OSG was moved away from Globus. So that's my concern.
Ryan, for projects that already have time allocations on Theta, for example, what is the model for such a project being able to make use of this sort of technology?
Yeah, so at the moment, because we're not serving multi-tenant solutions, essentially we would work with somebody in that group to start a site manager, which we want to simplify as much as possible. So it's literally run a script, and it will start a site manager. It will deploy parcel and call back to the service to start receiving jobs. And then it will automatically start using the allocation of the user that started that site manager.
So that would mean submitting a batch job of whatever necessary size to obtain a set of nodes, and then they would be usable during the period of time you had those nodes?
Yeah, so the site manager would deal with all of that. It uses Parcel to actually acquire the nodes and use it as a pilot model to deploy the actual runtimes onto those nodes.
Is there any ability to dynamically scale the size of allocation?
Yeah, Parcel does scaling of allocations, yeah. Yep, you set it a max number of blocks that you want and an initial number of blocks, and then based on demand, if you start deploying more workers, so you specify how many workers you want, which is essentially how many runtimes you want on a specific block or on a specific node. And if you start exceeding that with more and more jobs, it will start acquiring more and more nodes.
Thank you.
So just a comment from possible use cases side. I mean, this looks like, just actually talking over to Jim real quick, this looks like a case where we might want to try something for the jagged array frameworks and see how much of that we can cast into Parcel. I think it could work out quite well. What's your take on that, Jim?
Yeah, I was interested in trying that as well, but I didn't want to speak for you. Yeah, I think we're interested in trying this as another use case. We have wrapped up our end user data analysis problems in a way that could possibly be expressed in Parcel. And it would be interesting to try it out. You said these things are in development. When would you be able to take on another use case like that? When would we be able to try to work together?
Yeah, no, I think that sounds really promising. So two things here. One is Parcel is fully fleshed out. So people use Parcel at millions of tasks sort of scale. So that's all done. FuncX is definitely under development. And also our high energy physicist, Anna Woodard, who used to work on CMS, I think. She's really our bridge into your community because I'll have absolutely no idea what you're talking about. She recently had a baby, so she should be back in the next month, I believe. So maybe we can start the process.
Or sorry. She's at UChicago, right?
Yep.
Okay, so you and I and Matteo should probably just make a visit to the campus and have an on-site meeting.
Yeah.
Yeah, definitely. It'd be great.
Great.
She would love that, and I've worked with her a bunch with Parcel, and she's very much open to collaboration.
Mm.
Great.
Okay, any other questions? And Ryan's email address is associated with the agenda, so if somebody wants to, and I'm sure you can, and it's right there on his slides as well, so anyone wants to get in touch, please do. If anybody's got, got an idea for another one of these topical meetings that they would want to see, we're always looking for ideas of people or topics to bring in. So please feel free to nominate others or self-nominate. Get in touch with myself, Brian Bachman, or Peter Elmer, or anybody else who's in the IRIS-HEP organization. But thank you very much, everybody.
Yeah, thanks a lot.
Yes, and thank you, Ryan.
Yep,
Yeah,
thanks.
no worries.
Yep,
Bye.
thanks,
Cheers.
Ryan.